The massive eruption of an underwater volcano in the Pacific has seen Tonga's capital flooded by a tsunami and covered in ash.
Volcanoes are devastating, especially the underwater kind known as seamounts. And these seamounts cover approximately 29 million square kilometers of the Earth beneath the sea. Some are docile, while others are waiting to explode at any moment. And the largest underwater volcano has suddenly erupted. It's over now. This eruption was 100 times stronger than the little boy nuclear bomb dropped on Hiroshima. What can we do against such forces of nature? Is there a way for us to avoid these events? Join us as we take a look at these seamounts and their devastating effects on humans. Bunt Cake Seamount. In early 2023, a team of explorers discovered an underwater mountain off the coast of California. They described this mountain as resembling a bunt cake. This bunt cake-like structure stands at a height of 3,200 feet. However, it is just shy of the recognized size for a seamount, which is a minimum of 3,300 feet above the surrounding seafloor, as defined by the National Oceanic and Atmospheric Administration. Although it doesn't precisely meet the height criteria, scientists have labeled this feature as a seamount. But before we go any further, what exactly is a seamount? These formations are underwater mountains characterized by steep sides that rise from the seafloor, representing the remnants of extinct volcanoes. Most seamounts, whether ancient or active, don't breach the water's surface. They're basically underwater volcanoes that don't reach the surface of the ocean. The interesting thing about seamounts is that they cover a larger expanse of the Earth's surface than either deserts, tundra, or other land-based habitats. Their attractiveness to marine life comes from their capacity to bring nutrient-rich water upward from the seafloor. These things serve as a hub for diverse underwater ecosystems. Typically cone-shaped seamounts can display additional features such as craters and linear ridges. Certain types, called guyots, exhibit large, flat summits. These formations primarily emerge near the boundaries of the Earth's tectonic plates or mid-ocean ridges, where plates spread apart, allowing magma to ascend and create volcanoes. Additionally, near subduction zones where plates collide, the descent of ocean crust into the Earth's interior triggers the formation of magma, eventually leading to the creation of seamounts. Seamounts form not only near plate boundaries, but also at hot spots, isolated areas within tectonic plates, where magma plumes rise through the crust and erupt on the seafloor. The Hawaiian Islands are a prime example of this phenomenon, arising from chains of volcanoes and seamounts. These submerged mountains exist in every ocean basin worldwide, and although the exact count remains unknown, they are plentiful. Satellite altimetry and bathymetric mapping data suggest that the number of seamounts standing at least 1,000 meters high exceeds 100,000. However, only a small fraction of these seamounts have been thoroughly explored, amounting to less than 0.1%. Off the California coast alone, there are at least 63 seamounts stretching along the coastline.
No deaths have been reported yet, but the situation in low-lying areas and outer islands is still unknown.
Most are situated over 100 miles offshore and a mile or more beneath the ocean's surface. While not presently active, these seamounts were active roughly 10 to 25 million years ago. Seamounts aren't just interesting for their geological facts, though. They're known for their distinctive ecosystems that have adapted to hydrothermal activity. Scientists say that seamounts are underwater oases for life in the deep sea. Research conducted on seamounts emphasizes their role as life havens. They exhibit higher species diversity and biomass compared to the flat seafloor, attracting unique marine life to their elevated locations in the water column. Seamounts influence water current patterns that impact the ecosystems thriving on and around them. These structures rise from the ocean floor, so they significantly influence the ocean environment. Their rise shapes ocean currents, channeling nutrient-rich deep waters upward along their sloping sides, creating highly fertile habitats for diverse marine life. These structures also act as a substrate for organisms to settle and develop. A substrate is a location for attachment for organisms. Seamounts create a food source for various other marine animals. Scientists have identified endemic species found exclusively in a specific area among the rich biodiversity that inhabits these seamounts. These habitats accommodate various species, such as sponges, crabs, sea anemones, commercially important fish, and deep-sea corals. In contrast to shallow water corals relying on photosynthetic algae and sunlight, deep-sea corals derive energy from filtering organic material sinking from the surface. These features provide solid foundations for deep-sea life to settle and flourish. One of the most extensively studied seamounts is the Davidson Seamount, distinguished as the first underwater peak designated as a seamount. Located approximately 50 miles off the Big Sur coast, it has a unique, elongated arrowhead shape composed of steep volcanic cones primarily formed around 15 million years ago. Comprised of Hawite, Marguerite, and alkalic basalt, common among ocean island volcanoes and spreading ridges, these cones occupy a volume of 320 cubic km. Like seamounts giving rise to islands by breaking through the ocean surface, the Davidson Seamount remains entirely submerged, with a visible crater at a depth of 1,200 feet below sea level.
Yesterday evening, the Hunga Tonga Hunga Ha'apai volcano exploded. It's just 70 kilometres north of Tonga's capital, Nuku'alofa.
But let's go back to this unnamed seamount off the coast of Northern California. This particular seamount diverges from the typical conical shape seen in many seamounts. According to Aurora Elmore, NOAA's Ocean Exploration Cooperative Institute program manager, the Davidson Seamount stands out due to its steep, tower-like rise from the seafloor. This is completely different from the more gently sloped structures similar to Mount Fuji seen in other seamounts. The discovery. So how did scientists even find this oddly shaped seamount? It was thanks to a remote sailboat. The Surveyor SD-1200, an uncrewed sailboat fitted with multi-beam sonar, operates using remote control from the company's base in Alameda, methodically surveying the ocean depths to chart their contours. The sail drone surveyor navigated the challenges of storms to gather high-resolution bathymetry without endangering human lives. Brian Connon, Vice President of Sail Drone, believes that this approach is the future of ocean mapping. So, what makes this sailboat so special? Equipped with wind-powered propulsion and solar-driven meteorological and oceanographic sensors, Sail Drone Uncrewed Surface Vehicles, or USVs, collect precise ocean data across diverse applications, even in the harshest maritime conditions. The maritime security variations of these vehicles integrate sophisticated acoustic and camera systems along with proprietary onboard machine learning technology to provide enhanced information and decision-making advantages around the clock. The Sail Drone Surveyor, recognized as the world's largest uncrewed ocean mapping vehicle, identified a peculiarly shaped seamount situated 200 miles off the Northern California coast, extending beyond the typical seamount locations found near coastal regions. Aurora Elmore commented that this discovery enlarges the known range of seamounts, meaning we might find more if we keep searching around this range. This seamount rests approximately 184 nautical miles from Cape Mendocino, about 300 miles northwest of Sacramento. Past radar and satellite data hinted at a possible protrusion from the seafloor in the region, but the discovered seamount revealed a larger feature in the area. Positioned between the Mendocino and Pioneer fracture zones, the seamount resides in a highly dynamic region. It doesn't make sense to experts that this seamount wasn't discovered earlier. To them, this zone is very intriguing due to its fault-related characteristics and its close proximity to numerous ocean science institutions. But there has been a lack of exploration efforts despite this fact. Either way, we eventually found it. This bunt cake-shaped seamount has intrigued scientists with its distinct roundness, steep sides, and a curved summit sloping into a central crater. Nia Bachelor, a hydrographer with the Ocean Exploration Trust and lead surveyor for Sail Drone, noted its unique form, mentioning the top's slight asymmetry and the 352-foot depth of the summit, with a 200-foot deep central crater. The formation structure, resembling a tall donut, has scientists wondering about its origins. They have a few theories, though. The shape could be the result of rapid volcanic activity or the accumulation of marine debris, even humorously referred to as a millennia of fish poop by the explorers. They think this may have contributed to the steep slopes. While similar formations exist on the ocean floor, discovering one nearly meeting the seamount size criteria is a rare occurrence. According to Aurora Elmore from the sail drone team, the distinctiveness of this seamount stands out within the predominantly volcano-formed structures typically found on the ocean floor. Its crater-like appearance suggests that it may have started out as an underwater volcano. John Copley, a professor of deep-sea ecology and ocean exploration at the University of Southampton, also chimed in on this discovery. He said that it's extremely rare to find something like this, and it's exciting that we have. Seamounts like the bundt cake-shaped mountain are rare in the deep sea.
This is the moment that a volcano erupts underneath the sea.
Because usually, in the deep sea, you'll find loose, muddy sediment. These seamounts have rocky, hard surfaces. This is something marine life values a lot, considering that these places also serve as attachment points for them. The steep sides of seamounts don't allow mud to accumulate, and this unique environment supports the growth of filter-feeding organisms, deep-sea coral, and sponge gardens. Determining whether this seamount officially qualifies as such will likely be the responsibility of the committee that names underwater features. The General Bathymetric Chart of the Ocean Subcommittee on Undersea Feature Names, operating under the International Hydrographic Organization and the Intergovernmental Oceanographic Commission. They will make this decision, but until then, this seamount is unnamed. We don't even know if it'll even be referred to as a seamount in the future. Why are seamounts important? The sail drone surveyor discovered the seamount in February 2023 during its mission, which began in July 2022. The vessel initially mapped the previously unknown seafloor contours around Alaska's Aleutian Islands before moving along the California coast. Brian Connon, Vice President of Ocean Mapping for Sail Drone, highlighted this discovery as a prime example of the hidden treasures awaiting exploration in U.S. waters. The mapping expedition also revealed other intriguing features, such as long finger ridges, submarine canyons, and basins. Sail Drone plans to submit data about the seamount, which will ultimately add it to international maps as a recognized feature. While adding to our stockpile of undersea knowledge sounds exciting, the question still remains. Why are seamounts important? What is it about them that warrants dedicating so many resources, manpower, and technology? Seamounts, despite often being hidden beneath the ocean, serve as crucial geological features, offering deep insights into the planet's shaping forces. These undersea formations, shaped by volcanic and tectonic processes, present targets for mining companies eager to extract minerals resulting from hydrothermal activity. These formations are full of life. That means they are essential fishing grounds for over 80 commercial species globally. However, they face threats from destructive practices such as coral mining and fish trawling, which leave long-lasting scars in these diverse ecosystems. Seamount habitats, hosting over 1,300 animal species, were largely unexplored until their discovery in 2000. Scientists are just beginning to unravel their ecological significance and impact on deep-sea life evolution. Researchers are delving into the relationship between seamounts and ocean currents, investigating their role as hubs for unique species formation and biodiversity. However, while seamounts hold great biological value, they are also sensitive to human disturbances like fishing and mining due to their isolated nature. Scientists are wondering if seamounts are havens or transitional zones for sea life in the huge expanses of the ocean floor. Studies also aim to understand how seamount populations adapt to changes induced by shifts in ocean circulation due to climate change, as well as the potential for habitats disrupted by human activity to recover. These investigations provide vital knowledge on these undersea formations and their role in supporting diverse marine life. The more we learn about this, the more we can stay informed. And this knowledge is especially important for policymakers. When we gain in-depth knowledge of how our activities affect marine, policymakers can make decisions that can preserve the ecosystem in the long run. Hunga tonga hunga ha'apai. Now, it's not always about preserving nature. Sometimes humans are the ones that need safeguarding from nature itself. While this unnamed seamount seems harmless, others pose a very real threat, such as the HTHH eruption. The eruption of Hunga Tonga Hunga Ha'apai in the Tonga archipelago on January 15, 2022, has been one of the most significant volcanic events of this century. Situated among the 170 islands of the Kingdom of Tonga, about 65 kilometers north of Tonga Tapu, the capital's host island, the eruption severely impacted the region. The disaster severed crucial communication lines and isolated the islands, primarily due to damage to the main telephone and internet cables. The resulting tsunamis caused severe damage across the archipelago, particularly affecting Mango Island. The impact extended far beyond, reaching Japan and parts of the North and South American coasts. Fortunately, swift action and evacuation measures led to a low casualty count, with only 3 reported deaths in Tonga and only 2 in Peru. However, over 80,000 individuals were significantly affected. The aftermath involved complete ash coverage, crop destruction, water contamination, and health risks due to respiratory concerns for the affected population. But before we get deeper into the devastation of this event, let's talk about the volcano itself. Hunga Volcano resides within the Tonga-Kermadec intra-oceanic arc in the Pacific, formed due to the subduction of the Pacific Plate beneath the Indo-Australian Plate. This subduction system stretches approximately 2,550 kilometers from New Zealand to Tonga. Hunga Tonga Hunga Ha'apai's geological structure comprises a submerged colossal volcano extending more than 1.8 kilometers in height and spanning roughly 20 kilometers across the seafloor. Its most prominent feature is a large caldera at its summit, measuring approximately 5 kilometers in diameter. Before the 2014-15 eruption, the small islands of Hunga Tonga and Tonga Ha'apai emerged from this caldera. Following the 2022 eruption, only fragments of these former islands remain, with just Hunga Tonga and Hunga Ha'apai partially visible above the ocean's surface. The kind of rock Hunga Tonga Hunga Ha'apai erupted is known as andesite. This is common for this type of volcano. But what isn't common for this type of volcano is the fact that it can have caldera-forming eruptions. Something like this is quite rare. These calderas are immense volcanic depressions, often circular, with a diameter significantly larger than that of the included vents where lava gushes out. The formation of calderas can arise from the collapse of a shallow magma reservoir's roof, often post-eruptions involving substantial magma volumes. Eruptions are bad enough, but caldera-forming eruptions are even worse. Such eruptions can be catastrophically impactful, as seen historically with volcanic events like the Krakatoa eruption in 1883, which resulted in destructive tsunamis and a death toll in the tens of thousands. This goes to show that we need to better understand how these eruptions are triggered. If we do, then we may be able to save thousands of lives in the process. The eruption. The eruption of Hunga Tonga Hunga Ha'apai set off a series of extraordinary events. The volcanic explosion deposited heavy ash, sometimes solidifying into rock on the nearby islands. The explosion and the shifting of the seafloor generated powerful tsunami waves that snapped the undersea communications cable to Tonga, isolating it from the world. The ash from the eruption hindered satellite communications due to its presence in the atmosphere. The sonic boom from the blast reached as far as Alaska, and the tsunami flooded the islands in the Tongan chain, causing death and destruction. In Tonga alone, 4 people perished because of the tsunami. NASA's Goddard Space Flight Center estimated that the eruption had the power equivalent to exploding 4 to 18 megatons of TNT. This is hundreds of times more than the atomic bomb dropped on Hiroshima in 1945. While it was the most powerful volcanic eruption since Mount Pinatubo in 1991, it was only half as forceful as the Mount St. Helens explosion in 1980 and far less potent than the massive 1883 Krakatoa eruption, which had 10 to 20 times more energy. Beyond the lightning's sheer intensity, what fascinated researchers was the occurrence of concentric rings of lightning expanding and contracting within the plume over time. Van Eaton expressed astonishment at the scale of these lightning rings, noting that while single rings have been observed, They are typically much smaller and far less numerous in meteorological storms. Researchers have identified around 42 volcanoes worldwide with the potential to erupt like Hunga Tonga Hunga Ha'apai. They suggest that the powerful high-altitude turbulence generated by the volcanic explosion played a significant role in this extraordinary lightning event. The vast material propelled upwards during the eruption rapidly ascended to its maximum height, creating an expansive umbrella-shaped cloud spanning over 186 miles wide. The force generated by the explosion caused the material in the plume to continually overshoot into the stratosphere, forming rapid-moving concentric ripples known as gravity waves, akin to dropping pebbles in water. Lightning appeared to follow and expand along these waves, creating a pattern of 155-mile-wide rings. Van Eaton emphasized the impressive discovery that the lightning rings were associated with gravity waves moving through the volcanic plume. This marks the first time data has shown how a powerful volcanic eruption can establish its own weather system, sustaining conditions for electrical activity at unprecedented heights and rates. Rowley, not directly involved in Van Eaton's study, speculated that in significant eruptions, such concentric rings and gravity waves of ash might often be followed by lightning, potentially more frequently than previously understood. However, he suggested that further data is necessary to confirm this occurrence. The lightning activity was not only a nice visual spectacle, but it also provided insights into the sequence and phases of the Hunga Tonga Hunga Ha'apai eruption. The eruption was delineated into 4 distinct phases, observable from the fluctuating lightning rates corresponding to changes in the plume's height. The initial phase involved a small plume that didn't attract much attention. Subsequently, the eruption intensified, ejecting a vast volume of rock, ash, and sediment, equivalent to the material needed to construct the Great Pyramid of Giza nearly 3,800 times. In the third phase, the eruption continued, but at a lower intensity, with the plume's height diminishing to about 19 miles, still an extraordinary elevation. Following this phase, there was an intriguing pause, suggesting a lull in the volcano's activity, before the eruption gradually decreased in intensity during the fourth phase. It's very significant for researchers to see the final phase of the eruption, particularly for those involved in forecasting ash emissions and their movement through the atmosphere. Following the eruption of Hunga Tonga Hunga Ha'apai, the extensive ash cloud traveled approximately 1,860 miles westward to Australia. This ash can affect local water supplies where it settles and can impede relief efforts. Additionally, volcanic ash disruptions pose substantial financial costs to airlines. This happened in 2010 with the Icelandic volcano eruption on the aviation industry. Accurate information about volcanic plumes at the eruption's onset, especially for remote or submarine volcanoes, remains challenging to obtain. However, the data gathered from the Hunga Tonga Hunga Ha'apai eruption may aid meteorologists in monitoring and predicting aviation-related hazards resulting from explosive volcanic activity, such as ash cloud development and movement. The unexpected and impactful nature of the Hunga Tonga Hunga Ha'apai eruption shows the global hazard posed by large-volume volcanic eruptions, as cautioned by David Tappan, an expert on volcano-triggered tsunamis. He says that it's very important to prepare for similar events, especially considering that approximately 42 volcanoes worldwide hold the potential to erupt with a magnitude similar to Hunga Tonga Hunga Ha'apai. This unprecedented eruption has prompted a reassessment of communication methods among scientists. Van Eaton says that there were weeks of lower-level plumes before the eruption intensified. This shows how unpredictable volcanic events can be. The devastation. Now that we have a clear picture of the magnitude of this event, what sort of destruction did it result in? The volcanic eruption and resulting tsunami in Tonga inflicted severe devastation, leaving communities in ruin and covered in layers of ash. The government of Tonga described the event as an unprecedented disaster. The country's communication infrastructure was severely disrupted, with the single undersea cable connecting Tonga to the rest of the world severed during the eruption. The port in Nuku'alofa, the capital on the main island of Tongatapu, suffered extensive damage, especially along the waterfront, where many buildings were flattened. While the waterfront in Nuku'alofa has been heavily impacted, reports suggest that inland areas largely escaped serious damage. However, the United Nations reported substantial property damage on the western beaches of Tongatapu, where waves as high as 15 meters struck the area, resulting in significant destruction, including severe or complete damage of 56 houses.
We are preparing our Defence Force assets to support any relief effort that may be required.
Australia and New Zealand are both planning to send surveillance planes tomorrow morning, provided the ash cloud has cleared.
Affected residents relocated to evacuation centers. There was growing concern for the inhabitants of smaller, low-lying islands to the north of Tongatapu. Reports indicate the complete destruction of homes on one island, with about 50 residents and only 2 houses remaining on another, along with significant damage on several other islands in the region. The primary airport for the islands, Fuamotu International Airport, remained undamaged, but the presence of ash piles impeded airport operations and international aid efforts. This meant that clearing the runway was a priority. Efforts were underway to clear the runway for planes to land and deliver necessary supplies and support. Countries such as Australia and New Zealand mobilized aid and resources, with New Zealand dispatching 2 ships carrying water supplies, survey teams, and a helicopter. Satellite imagery shows minimal land remaining above water at the site of the eruption, indicating extensive destruction of Hunga Tonga Hunga Ha'apai as a result of the volcanic event. It was a magma hammer. There was a surge of magma that rose right beneath the seamount on the day of the event. And this happened during the first 10 minutes of the eruption. This magma entered into the chamber and overpressurized it. It happened at such high speeds and with such ferocity that he compared it to a train hitting a wall. And it didn't just happen once. The magma hammered the wall 4 times within 300 seconds. Each blast had a force of 1 billion metric tons. This eruption was the biggest atmospheric event ever recorded by modern instruments, surpassing any post-World War II nuclear test. The eruption itself moved about 10 cubic kilometers of rock, sediment, and ash. And all of this was flung into the sky like a shotgun blast, according to one geologist. The pressure waves circled the Earth 3 times in a row. On the other hand, Krakatoa's pressure waves circled the Earth 7 times in a row. But that doesn't downplay the immense magnitude of this event. And we already know that the ash from the eruption reached 57 kilometers above the Earth. This was measured by weather satellites and was determined to be the highest volcanic plume ever recorded. But it might have gone even higher than that. According to Dr. Larry Paxton from the Johns Hopkins University Applied Physics Lab, sensors on NASA and US Air Force satellites, designed to measure far ultraviolet radiation, detected a significant absorption correlated to an altitude above 100 kilometers, the Kármán line, indicating that material had ascended above the boundary to space, covering an area as vast as Montana, Germany, or Japan. The eruption also led to substantial lightning activity, including an exceptional gamma-ray flash detected by NASA's Fermi spacecraft. This unusual occurrence marked the first time a volcanic flash had been observed from Earth, using instruments intended for capturing high-energy emissions from distant phenomena like black holes or exploding stars. The explosions generated multiple pressure waves that passed through weather clouds at a speed of 300 meters per second. The largest explosion's shockwave, however, traveled across the planet, causing a sonic boom that was heard at significant distances, including within approximately 2 hours in New Zealand, Samoa, Fiji, Vanuatu, the Cook Islands, and Alaska. These pressure waves were also detected by infrasound and weather instruments globally, circulating the Earth and being picked up again upon their return from the opposite direction. This volcano is known for erupting. History reveals on and off activity, with recorded eruptions in 1912, 1937, 1988, and later in 2009, leading to an increase in land area at Hunga Ha'apai. Subsequent activity in December 2014 and January 2015 resulted in the merging of the islands, forming the combined Hunga Tonga Hunga Ha'apai Island. The recent eruption in January 2022 was particularly intense, significantly altering the landmass formed during the 2014 to 2015 eruption. Let us know if you think this is the end of this volcano's activities, or if there will be more in the future. Leave a like and subscribe for more.